Hey everyone, welcome. Today, we're going to tackle a really cool chemical mystery, one that had scientists scratching their heads for a long time. And the best part? We're going to solve it together, using one of the most powerful ideas in all of chemistry.
So chemistry has all these beautiful, elegant rules that usually work perfectly. But every now and then, you run into something that just doesn't fit. And there are a couple of these big, fundamental questions that the standard theories, for the longest time, just had no answer for.
Okay, so here are the big puzzles. First one, why is liquid oxygen magnetic? I mean, the stuff they use in rocket fuel, why does it literally stick to a magnet? And the second one, why can't you get two helium atoms to form a molecule? We're talking about helium, the second most common element in the entire universe. You'd think they could team up, right? These are some seriously basic questions, and yet, no easy answers. Yeah, for a long time, the go-to tool for chemists trying to explain bonds was something called valence bond theory. And look, it's great for a lot of things, it really is. But when it came up against these two specific puzzles, it just hit a brick wall. It had nothing. So valence bond theory, or VBT for short, it's got this pretty simple idea at its core. It says electrons are shared between two specific atoms, and that's what makes a bond. But here's the thing, that's exactly the problem. This really narrow, localized view just can't explain why oxygen is magnetic, and it has no clue why helium atoms refuse to form a molecule. It was pretty clear we needed a bigger, better idea. And then, in 1932, that bigger idea finally showed up. And to solve this mystery, we're going to have to learn to think about molecules in a totally new way. And that new way is called Molecular Orbital Theory, or MOT. And its big, game-changing idea is this. Forget about electrons belonging to just one atom. MOT says that when atoms bond, their individual orbitals merge and create brand new molecular orbitals that belong to the entire molecule. The whole shebang. Yeah, this quote absolutely nails it. In MOT, the atoms kind of lose their individual identities. They're not the main characters anymore. They fused into something new, and their electrons are now playing for the whole team. It is a complete and total shift in thinking. Okay, so let's get into the nitty-gritty. How does this whole merging of orbitals actually work? Well, it all comes down to this really simple but super important split. So here's the deal. When two atomic orbitals come together, they don't just average out. Instead, they split and form two totally new molecular orbitals. You get one that's low energy and really stable. We call that a bonding orbital. And you get another one that's high energy and much less stable. That's the anti-bonding orbital. And you can actually see what these look like. The bonding orbital down at the bottom, that's sigma. It concentrates all the electron glue right between the two atoms, pulling them together. But that anti-bonding orbital up top, sigma star, it does the exact opposite. It yanks the electrons away from the middle, basically trying to push the atoms apart. It's this constant tug of war between these two forces. All right, so we've got our new orbital energy levels. The next step is to fill them up with electrons. And just like when you're dealing with single atoms, there are a few simple rules we've got to follow. Think of these as the rules of the game. Rule 1, you always fill the lowest energy orbitals first. Start at the bottom, work your way up. Rule 2, you can only put two electrons in any one orbital, and they have to have opposite spins. And rule 3, this one's important. If you have a bunch of orbitals at the exact same energy level, you put one electron in each before you even think about pairing any of them up. That's it. Pretty straightforward, right? Okay, we've got our theory, we've got our rules. It is time to put this new toolkit to the test. Let's see how this whole framework just completely solves those mysteries we started with. This is the payoff. Let's do it. All right, let's start with helium. A helium atom has two electrons, so a hypothetical H2 molecule would have a total of 4. Now, following our rules, the first two electrons go right into that low-energy bonding orbital. Great, but where do the next two go? Well, they have no choice but to go into that high-energy, destabilizing anti-bonding orbital. So, what does that actually mean? Well, to figure that out, we can calculate something called bond order, and the formula is super simple. You just take the number of electrons in your bonding orbitals, subtract the number of electrons in your anti-bonding orbitals, and then divide the whole thing by 2. This one little number tells you pretty much everything you need to know about how stable that bond is. So for our imaginary helium molecule, that's 2 electrons in the bonding orbital minus 2 electrons in the anti-bonding orbital. 2 minus 2 is, of course, 0.
and half of 0 is, well, it's 0. And bam! There's our answer. A bond order of 0 means that the glue from the bonding electrons is completely canceled out by the push from the antibonding electrons. There is absolutely no advantage for those atoms to stick together, so the molecule just falls apart. Or rather, it never even forms in the first place. Mystery number 1 solved. All right, 1 down, 1 to go. Let's move on to oxygen. Now, this one's a little more complicated. There are more electrons to deal with. But if you just follow the same rules, fill from the bottom up, your eye should go right to the top of the diagram. See those two orbitals that are at the same energy level? Pay very close attention to where the last 2 electrons end up.
This is the whole key. Remember Rule 3, Hund's rule? It says when you've got orbitals at the same energy, you give 1 electron to each before you double up. And that's exactly what's going on here. And the result of that is huge. The oxygen molecule has 2 electrons sitting all by themselves in separate orbitals. They are unpaired. And that, my friends, is the textbook definition of something called paramagnetism. Any molecule that has unpaired electrons will be attracted to a magnetic field. So molecular orbital theory doesn't just kind of explain this, it predicts it perfectly. And just like that, mystery number 2 is solved. And this is just a beautiful way to see the power of this theory. Just look at the comparison here. On the left, we have nitrogen, N2. See how all its electrons are neatly paired up? Not magnetic. But on the right, you've got oxygen, with its 2 unpaired little troublemakers. And that is why oxygen is magnetic and nitrogen isn't. It's a subtle difference, but MOT explains it perfectly. So, let's wrap this all up. We started out with these 2 really stubborn mysteries that the old theory just couldn't handle. And we solved them just by looking at what a chemical bond really is, from a completely new angle. I mean, this final scorecard really says it all, doesn't it? Where valence bond theory just failed, molecular orbital theory came through. It explains the magnetism, it explains why some molecules just don't exist, and it even gives us a number, the bond order, to predict how stable a bond will be. It's just a way more powerful and complete way of looking at things. And that kind of leaves us with a bigger question to chew on, right? In chemistry, we saw that shifting our focus from the individual parts, the atoms, to the whole picture, the molecule, unlocked this way deeper level of understanding. So it makes you wonder, what other tough problems, maybe in science, maybe somewhere else entirely, could we solve if we just managed to stop focusing on the individual parts and started looking at the whole picture? Something to think about. Thanks for joining me today.